Okay, hi everybody. May I ask to turn on your camera, please? Thanks. More of you, if you could. So today, the plan is to discuss quiz 2. I look at your answers, and I would like to us to understand like a few things. Maybe refer back to what we discussed somehow. So hopefully you get a sense about this important topic in computer architecture, mainly performance, because it is fundamental. And I somehow designed this quiz for you to understand this aspect, this topic in computer architecture better. One thing I wanted to clarify for you, and that was intentional, this type of quiz, the question that you saw in this quiz, you had in this quiz, mainly to somehow enforce you to think a little bit, do some analytical thinking. This is very important. I mean, beyond this course, very important for you guys. When I'm also thinking myself, reflecting back when I was like you, an undergrad student, the type of thing that I still remember was not really, or I enjoyed, was not really the style, the questions, the courses that like enforces me to remember things mechanically, to do the things mechanically. Rather was the part of topics, the part of material that enforces me to think somehow. And when I found at least a partial solution, I enjoyed it rather than like the type of question when I get, even if I answer it correctly, fully correctly, I did not learn anything new. It was somehow mechanical thing that I did. So this type of question, when sometimes you see maybe it's somehow different from the rest of the other style that requires you to remember things rather than do analysis, rather than do some bit of thinking. I also looked at some of your responses on this question, and we will discuss in detail. So let's have this session more interactive, and please interact, engage, so hopefully you understand and learn. Again, like don't worry about the grade and everything. It is important really for you and for me to learn something, so you can take away something new, and hopefully, I'm sure you will do great in the other quizzes, homework, midterm, and final. If you really wanted to understand and fully grasp the content of this course. Okay, so let's go ahead and discuss what we have in this quiz. Can you see the screen? Okay, great. So the first question, performance analysis, and I have to mention these questions were a little bit tricky, and that was on purpose. That was really on purpose, not really aiming to trick you, but really enforces you to think. So the question is that when a single cycle macro architecture or machine is a good choice, and why? Okay. Provide an analytical answer, and I provided a hint: performance analysis formula and performance trade-off. All discussion about performance trade-off that we had multiple times throughout this course. Okay. So let's think about the question itself, right? When a single cycle macro architecture is a good choice, right? Meaning that, as you remember, by default, we discussed previously in the part of the lecture that we finished on Tuesday, single cycle macro architecture. Now from now on, we move toward multi-cycle. Somehow you see that the topics that we will cover from now on, it's somehow improving performance with respect to single cycle kind of architecture. And as we go also, we'll discuss some topics that enhances performance, improve performance, but by different techniques as we will move forward throughout this course. Right, that's the kind of framework you can think about. You will see throughout the next lectures until the end of this course. Hopefully, I wish we had more time to cover much more interesting topics, but we have to end this. But from now on, you will see, like, you can think about all lectures from now on somehow improving performance in that aspect, right? So single cycle architecture, we discussed that it has some shortcoming. And again, we start by single cycle macro architecture, and like you might ask, okay, like why it is, why if it is a bad choice, why we ever wanted to learn about it. And again, this is important because it's simple, like the few other topics that we discuss, like data flow, some other topics that somehow there is no realization of these things in practice. There is no like single cycle macro architecture or some of the other, but these things help you to, or for example, even LC3 as a microprocessor, there is no commercial realization of that, but why I wanted to understand this, because like it's simple. It somehow help us to understand the simplicity, and when we go into more practical, more like interesting aspect, we appreciate those and we understand like why, for example, when we move to multi-cycle, we understand like, okay, what is the benefit of multi-cycle macro architecture? So this contrast again is very helpful. So like this question, you should contrast it. Okay, like you should, the first thing you could think about it, like why single cycle microarchitecture is bad. And we have already discussed this, right? Let's maybe discuss this to understand this, like the stuff that I have here. We already discussed, but I want us to recall again. And at this point, when you see this question and when you thought about it, like now I'm sure you will understand this material better, right? So we discussed about like architecture, state, right? All of this, right? The memory, the program counter, the registers, and all of this, and contrasting of single cycle to multi-cycle type of machine, right? Again, in single cycle, each instruction takes a single clock cycle, right? So no matter what instruction we have, whether a very simple instruction like no op, like adding, or very complicated instruction, where it requires having access to the memory maybe multiple times. And like this is hinting to the other questions that we will discuss, right? Part of this quiz. So we have different types of instruction, simple, complex, but no matter what, we have only one single clock cycle for all of this, okay? And when we design a machine, a single cycle machine, like we have no choice, and we discussed this previously, we have no choice rather than determining the clock cycle based on the slowest instruction, right? Let me also visualize this. So this might be helpful. Again, please pay attention to what we discussed today, hopefully, because some of you are somehow lost. I got email from a few of you that you're lost. You shouldn't be actually, the way how we discussed so far, but these things happens. Okay, so if you think, right, so imagine that you have multiple instruction, and again, this is, imagine this is time, okay, this is time, like for example, this is instruction one, like somehow simple instruction. We have like another instruction number two. We have like another instruction number three, and we have like instruction number four. Okay. And like instruction number five, and so on, right? So like you have some instruction quicker, like this one is really this instruction in terms of time that it takes. It's really quick because like it's a no-op or is very simple instruction, but some instructions are complex or require accessing to the memory, like a store word or load word, and like by default you know that this memory is slow, right? When we compare, like think about like Mips instruction, like store word, load word require to having access to the memory multiple times, more than one, right? More than one, right? Some instruction, they only require access to the memory once, right? So memory is slow, and obviously you've got some of these instruction by default, which takes a lot of time. And the instruction that determine the cycle time is this guy, right? So this is the slowest one. So the cycle time, right, is determined by this instruction. We'll discuss more. Again, I would like to discuss more about performance analysis shortly in detail. So hopefully you understand it. We have discussed this before with some examples, but I would like to iterate it again. So like for those who did not, so hopefully you understand this. So in this case, this slow instruction determines the cycle time. And let's probably now discuss. Now it's a good time to discuss about performance before even going some of the detail of single cycle versus multi-cycle, right? Let me see. And yeah, before going to performance, let me mention something else as well. So going back to the slides. So that was single cycle, right? So in multi-cycle, we hope that we did not even started yet. We will from next week about multi-cycle machines. The hope is to break down into a smaller stages. The key idea, really the core idea of multi-cycle is to, as opposed to like having a situation where the cycle time is determined by slowest instruction, we want to give as much time as possible for each instruction, no matter whether it is slow or quick, right? So we want to have a smaller stages, right? So if an instruction if an instruction is very quick, is instruction very efficient, it obviously requires a lower number of stages. If an instruction is complex, we give it more stages, more of these smaller chunks. So we allocate more of these smaller chunks to let it execute. So somehow, if you think about this, and this is, let me also again, going back to these visual things. And by the way, again, like whenever you require, you have a question, please do ask it. It is important to understand it fully. So here, what we had was like we had like for this, we had this large chunk. This is cycle, right? The same cycle for this, 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 right? The same cycle for this, the same cycle for this, okay? So what is the vestige that we have here, right? Like all of these are wasted. Like we allocated the time for this where this instruction only used this part of it. The rest was wasted. The rest basically, the CPU, the whole machine was waited like doing nothing, but like it couldn't proceed, it couldn't do anything else, right? This is the same for this, same for this, the same for this, the same for this. It was even very long wastage we had here. The only instruction that did not have any waste, it was this one, number 5, which was the slowest one. Like the slowest one, like took advantage of it, like, and it exploited the resources, and it enforces others to waste resources without doing anything. Okay, but in multi-cycle, the key idea is to, instead of having a fixed cycle, cycle again, like cycle has to be fixed, right? So we cannot have like a variable cycle time, right? Cycle time has to be fixed, right? This is determined by the clock, right? The clock, we cannot have like a variable cycle, right? But we can have stages, we can have a smaller stages to somehow emulate a variable cycles, right? So we can break down things, a cycle, into multiple smaller things. Let me use a different color. So imagine that like we have, we call this a stage, okay? We have these smaller stages, the same way as here, the same here, the same here, here, and also here, here, okay? What you see is that like a simple instruction such as this, like fewer number of stages, like 1, 2, like 5, whatever. And this a slow instruction, this complex instruction, like much more, okay? Like 20, right? So now we have a different instruction with variable number of stages that we can allocate to each instruction, okay? So with this new concept, with this new stage, we could allocate and we could somehow, instead of wasting, we give each instruction the required amount of resources as they need without wasting things, right? So that's the key idea of multi-cycle, having smaller stages in order to give each instruction, no matter whether it is complex or simple, in order to decrease the wastage of resources, okay? Now let's again, with what we discussed, to make a sense from the analytical perspective, why, right? So remember, what was the execution time? or performance. And by the way, remember, when we say performance, performance is a generic thing, and in some other courses, you may hear about performance. Performance means different thing. In the context of this course, performance, like now specifically about this slide, performance means execution time. But even in the context of this course, sometimes when we say performance, it might mean energy consumption, okay? So whenever you heard about performance, ask like, what is performance here? Or think what is exactly, what do we mean by performance? Like in the context of this specific slide that we are talking about, performance like means execution time. What was, how we calculate?
I have a question.
Yes, go ahead.
Does performance also relate to the amount of memory used?
Yes, performance also, exactly. Excellent question. Yeah, sometimes means like memory usage, right? Yeah, absolutely. But in the context of like what we are going to discuss in this slide, and with respect to this question, specifically we meant execution time, okay? But performance in general is a multi-aspect and like could mean like different things really depending on the context. So make sure you understand this. So how execution time is determined in general? We discussed this, right? So we have number of instructions, okay? Execution time or performance of a program, right? So so for this, let's formalize things better. We mean a specific program. Okay. For each program, we know that like we have a number of instructions to execute. So number of instruction multiplied by what? The number of cycle, right? Divided by each instruction, right? So this is what we had or what we called previously CPI. Okay, or cycle per instruction. This is, you can represent it mathematically. So cycle per instruction, okay? Is that clear? Multiply by what else? Time, right? You have time here, okay? And when you have a formula, right? You have to get the unit correctly, right? And we will explain it. Time per what? Per cycle. Okay, and let me explain it a little bit here. So think about this execution time, like we want to have a formula to give us the time, right? So it has to be a time, right? Why this formula makes sense? Like you have instruction, like this instruction with this instruction, this cycle with this cycle, time stays, so the unit makes sense, right? Think that way. So this again, right? And that's why this formula makes sense. And this was, again, the context of what we have discussed previously was we represented in the slide, I guess, with T, if I remember it correctly. Yeah, which was 1/f, which f is the clock speed of the processor, right? But essentially, these are both are the same, right? So time per cycle. So how much time we want to allocate for each cycle, right? So this is this might be using this might be more clearer and help you to understand this performance better. Okay, so let's now make a sense out of it, right? And let's now put it into the context of single cycle multi-cycle, right? So question. What is the factor that determine the number of instruction, right? For a certain program, okay, when we have a program, like let's say we want to calculate the factorial number, okay? We want to say, we want to add 10 numbers together in an array, okay? Whatever this program has, whatever specification we have about this program, what determines the number of instructions? Do you have an idea?
The amount of iterations that you do.
The amount of iteration. Okay, what determines the? So let me ask this question: could we have, like, for one particular program, could we have different number of instructions, like for the same very exact same program? Could you have
with conditionals? Yeah, of course. Like, I mean, it's like if it's two branches and one branch could contain much more code than the other. Like, it's just like return null if it's like an edge case versus like do everything else if it's not an edge case, for example.
Right, exactly. So like so we could have scenario for the same, like we could and like you have done it, like you already have experienced it, not only in this course but some other courses, programming courses. Like, you know, that for solving a program there are many different ways of solving it correctly. I'm not talking about like there are many different ways to solve a problem or implement a specification incorrectly. I'm not talking about it. But once we have a specification, like we have a specification here. For a specification, we can have like many different implementation. Implementation 1, implementation 2, implementation n, okay? So we can have like many different implementation, and all of these implementation are correct, right? But some implementation are better than the other one. Like this means that they are more efficient, okay? They run faster. And like, I'm not implying here like having more number of instructions would result running it slower. Not necessarily. You could have more number of instruction, but these instructions are type of instruction that like are running faster. and as a result, you get a better performance. But somehow the number of instruction really depends on particular implementation, right? So if you have a program, if you implement it in a clever way, you could get different number of instruction, right? So this factor, the number of instruction, really, even for one program, could vary from one program to another program. Between single to multi-cycle, like the number of instruction, we assume that like we have one specific implementation. We have like implementation number one, okay? We assume that the number of instruction are the same. Like when we contrast single cycle with multi-cycle, because we want to like take this away from the variable side. But really the number of instruction, even for one specific program, could affect the performance. And like, this is like where you see like clever implementation, efficient implementation of a program, right? So I want to understand this, right? Number of instructions, one important factor, but when we contrast single cycle with multi-cycle, we put that away. We explicitly or implicitly assume that we consider one specific implementation, where between these two, when we contrast it, we assume that the number of instructions are fixed. Is that clear? Okay. So now we are left with two species, number of cycle per instruction and time per cycle, okay? Let's focus on this, cycle per instruction, or CPI. We discussed this, like for single cycle, what was the assumption? In single cycle, what was the assumption for CPI? We assume it to be?
It's one cycle per instruction because it's a single cycle architecture.
Exactly, right? This is single cycle. One cycle per instruction. So this part of the formula for single cycle is already determined, one, okay? So this is clear. And for single cycle, we already discussed time per cycle. Really, this species is determined by the slowest instruction. So in this case, this is typically large. This is determined by slowest instruction in this case. So time per cycle is large. Okay, typically. In multi-cycle, what we have is that this CPI varies. Okay. Again, since we split it into these stages, so we could have an instruction that this number of cycle per instruction could be like for like, say we have like some instruction where CPI for instruction 1 might be 5, CPI for instruction 2 might be 2, CPI for instruction 3 might be like 1. Imagine CPI for instruction 7 might be like 100. Okay. CPI for instruction 8 might be 1000. Say CPI for 19 might be like, say, 10, whatever. So we have this variability, right? We have like different instruction having a CPI of like a variable CPI, okay? And the hope is to have time per cycle, a small time per cycle, right? So for each cycle, like you would like to be as fast as possible. So this time per cycle is this chance. Okay. And we already have a very specific example. If you remember, we discussed this previously here, right? If you remember this, we had an example where we had a certain number of instruction, right? And we had a certain cycle time, and we discussed an example where we had a program that was that had like 10 instruction. 9 of it was using fast instruction. Only one was this slow instruction, and we compared single cycle with multi-cycle, where this was the case for multi-cycle, where we could have variable CPI, and we calculated this average CPI by taking a weighted average of these. We discussed this, and if you do not remember, maybe go back and watch that lecture again. And do let me know if you want me to explain this again. I'm happy to discuss it. And at the end, like, we get a performance which was much better than single cycle, because in single cycle we were enforced to have CPI of 1 and having a larger cycle time. So as a result, the performance was like way larger than order of magnitude slower than the multi-cycle for the same program, right? And essentially here, like, the first factor was exactly the same, the number of instruction. The two factors that determine execution time was this these two terms, cycle per instruction and time per cycle. Yes, Ross?
So obviously, like, we're looking at this for like sufficiently large n. So like for multi-cycle, like presumably is always going to beat out like single cycle for like sufficiently like practically large n, you know, like on a realistic level. So it would only be like, if we like looked at it like arbitrarily small, could we maybe like see some time where like single cycle would beat out multi-cycle? Is that kind of like the idea? Because it doesn't seem like realistically with a reasonable like amount of instructions, however many it might be for like a reasonable program, like that it would multi-cycle would always beat it out.
Very good point. Very good point. So yes, you are getting to this particular question that we have, right? So, and we are discussing this to get to the point where, I mean, so far we have not discussed this question at all, right? So we wanted to make sense of this performance analysis to get back to the question, right? And contrasting this single cycle with multi-cycle. That's right. So think about it. Like in single cycle, could we ever, and that is a question, right? Could we ever really get close to multi-cycle situation? That's somehow the situation, right? This is a rewarding of the same question, right? So the question asked, so let me go back to the question. The question asked, when a single cycle microarchitecture is a good choice? You could ask it like when we can have the same performance as we could get with the multi-cycle architecture, right? How we could have like same or even better performance in some imaginary situation, okay? And really the answer lies in the performance analysis in this formula that we have, okay? Or you could also think about the visual aspect, however you are comfortable. When we can really have when we can really have a good performance in single cycle. Other words, what was the bad thing in single cycle, like this amount of waste? When we can have good performance, when the amount of waste is minimal, or when we don't have any waste. When we don't have any waste, can you answer that?
I think so.
Yes, go ahead, Bella.
Okay, so I think we'll have the least waste when all the instructions are very similar. When that difference is minimal, then we'll waste less time on single cycle because then it's less difference than every step in the multi-cycle.
Brilliant, brilliant. Exactly, right? So like we have the minimum waste or we have no waste, like absolutely no waste if all instruction taking the same amount of time, right? All instruction. So we get like no waste, right? So all instruction having the same amount of time, exactly the same amount of time, okay? Or at least as close as possible. If we want to like be not idealistic, as close as possible, right? In this case, single cycle is not really bad because all instruction taking the same amount of time and we don't have any waste. So the cycle time, like now imagine in this situation, we want to run this in multi-cycle, like other way, right? Ask yourself, like when you have situation, I mean, in typical computer, I mean, this situation is not typically happening. We could design a machine that has this situation. We could, but like realistically, we don't want to design it because essentially there are some limitations, right? If we want to have like division and add, mathematically, like division is more complex, right? So it takes more time, right? So there are, I mean, you could say, okay, we don't want to have like division in ISA. Yeah, that's fine. And like in some of these ISAs, we don't have division or like that. But essentially, like there are essential differences between instructions. But we are now talking imaginary, right? So imagine within this situation where we have instruction the same amount of time, we want to execute it in multi-cycle. What it happens is that does multi-cycle provide any benefit, right? So like we have this and we want to split it into these smaller stages, okay? So what is the average CPI in this case? Like what is CPI for this, right? You remember this scenario? Now, within this situation, what is the CPI for example, for I1? let's say 20. What is CPI for I2? What is CPI? Tell me.
Would it be 20 again?
Yeah, 20. What is for I3? 20. What is for 19? 20. All of it like the same, okay? So the CPI for all of this are 20, right? And what is the, so this is the, this guy. What is the time per cycle? Like whatever is a, say, is like 10 nanosecond, say, okay? Imagine 10 nanosecond for multi-cycle, CPI like 20. What is the, what would be time per cycle for single cycle? Can you tell me?
The time per cycle for single cycle will be the, it'll be the same for all of them. It'll be the longest cycle time of all of the different instructions.
Exactly. What would be the number?
In our case, it would be that, I believe it would be that 1,000 one that we had earlier, unless you're talking about the ones where it was all 20.
No, I'm talking about this situation where all instructions are the same.
Oh, all instructions are the same. It's all the same cycle time. They're all if it's the 20, it's going to be the 20 time. But if they're all the same cycle time, they're all going to be the same 20.
No, 21.
20 cycles per instruction. So 20 times the cycle time.
Oh, let me help you.
I think I got it.
Yeah.
Would it be 200 nanoseconds?
Exactly.
Okay, I didn't see I lost track of the 10 nanoseconds. That's my fault. Thank you.
So can you explain why, Bella, for others?
Sure, it's 200 nanoseconds because we have 20 instructions per cycle or per instruction, and each cycle takes 10 nanoseconds. So it's simply just 20 times 10, which is 200.
Exactly. So like here we assume that we have like multi-cycle. So we here like assume that like CPI for all instructions are 20, and this time per cycle is 10 nanosecond. Now, like when we want to like have the single cycle, like we know that the CPI is 1. So, and we want to have a fair thing, like the instruction time would not vary, right? Between these two. So like we should have like 20 times 10 nanosecond for the cycle time, right? In single cycle, right? So it would be, sorry about this, the whole mess. So it would be 20, 10 nanosecond, 200 nanosecond, okay? So this is the cycle, the time per cycle for single cycle, corresponding to exact situation that we discussed, right? So now, like, what is the performance? Like when within this situation, within given all of this, right? So when we have execution time of program 1, this program in single cycle, what is this? Like, yes, number of instruction. We assume that this is like, and what is the execution time of P1 for multi-cycle? Okay. we want to compare these two, okay? So the number of instruction, we assume these are same, right? So let's imagine like 10, okay? 10, okay? So here it would be the CPI, single instruction, CPI is 1, right? Multiply by, what is the CPI for this? It's 20, we assume, right? Multiply by time per cycle. We assume this is what? 200 nanosecond. So in total, we get what was the time per cycle here? For multi-cycle, it was, you see it here, 10 nanosecond. So here you get the same, right? So in this case, like we get the same execution time of single cycle and multi-cycle. Wow, okay. So we have a scenario where the execution time of single cycle, which was really, really bad, got the same, is the same with multi-cycle, right? And that's the answer, right? That's the scenario where these two are the same. But I mean, like there are some other factors that like we did not get at it, like and you will see in multi-cycle, there would be opportunity for pipelining, etc. But we have a like simple perspective, right? In this scenario, and like the aim of this question was really for you to think about this performance analysis formula, as I provided as a hint here for you, and think about like why single cycle is bad when it could be potentially good or get close to multi-cycle, and that was the whole goal of this. Yes, who had questions? Sorry.
I was wondering, so their performance time is the same. So at that point, what's the advantage of using single cycle if they end up the same at that point, or in this case scenario?
What would be the advantage of single cycle? Is this what you're asking, Stephen?
Yeah, so, well, you said their performance time is the same in this case. So at that point, does it matter which one you choose? Like, why would you choose single cycle?
No, like it doesn't really matter, right? So, but just, it was even like I mentioned this, like this scenario, like having instruction taking the same amount of time, like is imaginary. It's even though it's possible, really possible to have such scenario, but like would never happen, would never want to design such machine because of all reasons that we discussed, right? it doesn't make sense. But like having this formula, we could have this exercise, this imaginary exercise, making sense out of this performance analysis formula. That was the whole aim of this question. I wanted you to understand really this formula and deeply think about it. Yes, Ross.
So like, I'm not like just kind of bouncing off what he asked, and I'm not trying to like detract from the significance of all of this, but like, would single cycle ever actually beat out multi-cycle, or are we just approaching like the point where they can be equal, but it's like, would single, or like, would there ever be a point where it could surpass multi-cycle in terms of like how much time it takes? Like, would you have a situation where it's better?
Yeah, that's a very good question. And like for discussing about this, maybe the follow-up lectures would help you, and you will see like some benefit and some like downside of multi-cycle, right? In multi-cycle, and you will see like some pipelining that help you to make some parallelism happening, right? When you do like, remember, like you remember the microarchitecture. This is because this is such a good question. I want to take this opportunity to discuss this. You remember this instruction that we discussed? So let me, a very specific thing that we reviewed, like this is like the full macro architecture, right? Specifically, if you remember, we discussed this. We started with R-type, right? Where like this was part of the whole macro architecture, this complex machine which we require for executing R-type. Like even we don't have part of the memory which we put data in it, right? Let alone like if we go to jump, right? So with jump type of instruction, you remember with this, do you, I'm hoping you remember that, I mean, I was in a bad situation, but hopefully you remember that in jump, like the only part that matters was this part. We did not even need this part, right? So this was like idle. But essentially, like we could let some other instruction take advantage of this part, these resources, if they needed it. So we could enable some parallelism going on, and we'll discuss some of these as we go throughout this course. And also like the multi-cycle, you will see later on that it adds a little bit of overhead because of having like multiple stages. These multiple stages, meaning that we need to execute multiple combination of logic, which create a, somehow using multiple resources multiple times. So it has some extra overhead with respect to single cycle. In single cycle, like we saw the disadvantages of it, but like it's single cycle, but let's explain in detail, like when it comes to multi-cycle, you will see that it has some extra overhead, okay? So it's not the case that all the time there is no, like, there's always performance boost without any overhead. Like, and always remember, there is no free lunch. When you gain some performance boost, there always be a cost that you need to pay, okay? So you will see that, but that was a very good question to ask. Hopefully that answers your question.
I have kind of a follow-up question on that.
Yes, go ahead.
So if I understand correctly, it can be more simple to implement a single cycle machine. Is that right?
It's a lot simpler. Yeah, of course.
Okay, so that would be considered an advantage of single cycle, is implementation is more simple?
Yes.
Okay, awesome, thank you.
Sure. Any other question?
Yeah, I kind of have something.
Yeah, go ahead.
Okay, so we keep on saying that single cycle or this case scenario wouldn't happen, but wouldn't it happen in an item where it was a very repetitive similar command, like a tally counter or something in assembly line?
Yeah, absolutely. Perfect. Yeah, perfect. Thanks. Yeah. I mean, like in those situations where there are situations where we don't need a variety of many different instructions because of like we have a certain purpose, like for a specific problem, when also we have massive number of microprocessor we want to manufacture, and these are for like very simple tasks that doesn't really require a variety of instruction, and like few instruction that we need, they have like same amount of time. And in those scenarios, yeah, it makes a perfect sense. Yeah, that's perfect point. But what I was saying is that, like, for general purpose CPUs were really the general purpose, right? So we want to have this variety of instruction in order to enable general purposeness of these microprocessors, right? This situation, like, is not really, is imaginary, is not realistic. Very good question, thanks. Is there any other question that I can answer? So hopefully now you got an idea how you need to think about it and why it was important, right? And also this helped to let me get back to this slides. To the goal that we want to reach at the end, and also we will discuss this in more detail in multi-cycle, where we want to let each instruction take close to only as much time as they really need. And that's the kind of principle or the goal we want to achieve. And the idea is to determine the clock cycle time independently of instruction processing time, where it was imposed in single cycle. So in multi-cycle, by splitting this into multiple stages, we want to have the opportunity to determine the clock cycle time independently of the instruction processing time. And that's really important. And each instruction takes as many clock cycle as it needs to take, right? So these are like the key idea of having multi-cycle, okay? Sydney, Sydney is here. Are you here? Sydney Mayasaki, are you here in the class? Nope, she left. I think she was earlier here, right? Okay, so I wanted to mention that like this is the answer. This is the way she answered this question, which makes a perfect sense, and I liked it a lot. And let's read. This is a kind of analysis I wanted to see, right? She says that the main flaw with single cycle microarchitecture is the clock cycle time, which must be the amount of time taken to execute the slowest instruction. When it comes to CPI, single cycle always beats multi-cycle because it has a CPI of 1, which is the minimum possible. The number of instructions required to write a program varies upon particular program and the richness of the ISA. However, both single cycle and multi-cycle architecture can take advantage of this richness, and therefore the primary trade-off is CPI versus clock cycle time, right? This is what we discussed. If all the instruction in the ISA can be executed very quickly, right? If all instruction can be executed very quickly, then the clock cycle time for a single cycle architecture may be very low, right? Which is true. In such case, we want to optimize the CPI. Since the CPI must be at least 1 and CPI equal to 1 in a single cycle instruction, this situation is best suited for a single cycle microarchitecture. This is a good answer. This is not perfect answer because like she, I mean, I have to mention, especially for this question, like among all of you who answered, unless I missed some answer, this answer was the best that I could find. All other answers were somehow incorrect. But this is as close as you could get. It's not perfect. Why it is not perfect? Because she's not mentioning about like, it's not the case that like always having the instruction as quick as possible, but could be long, but having the same amount of time, right? The scenario that we discussed could take long, but having the same amount of time, this could get as close as possible to the multi-cycle scenario, and could make sense, right? But this answer is partially correct because of this. If we assume that this this instruction be as fast as possible, so this scenario is also correct. Somehow we could assume that all instructions are as fast as possible and equal, right? So this is also could be a correct answer. Hopefully this makes sense. And thanks again, Sydney, for answering this correctly. So this was the first question. Do you have any question with respect to this part? Okay, now let's move on to the other question, right? These are simpler. So about memory, what Mips instructions require having access to memory twice? And I have to mention, like, this was tricky. really indeed tricky question. Name as many as possible hint, instruction processing cycle, and semantic of Mips instruction, but I provided some hints, right? And the principle of one Neumann model, right? Again, principle of one Neumann model, like this is a good hint, like a stored program and sequential program execution, right? And instruction processing cycle stuff, right? So this was a good hint. And also, when you contrast it with the other question, like you should get it. You should get the answer correctly. Like here, like what Mips instruction do not require having access to memory at all, right? Okay, think about it. One Neumann model, the program is stored in memory. And think about it, where is this? So you remember this instruction processing cycle? This is exactly, it's in the hint. Fetch, decode, evaluate address, fetch operands, execute, store result. Okay? And like we discussed this like several times, right? Even like when we had Mips assembly. What's happening during fetch?
You're pulling from memory during fetch.
Yeah. So no matter what instruction and even we had this like in microarchitecture very recently that we discussed. Let me also go back to this. You remember we discussed this, right? And this is no matter like what instruction it is, for all instruction, like the first thing, we have access to the memory, fetch, instruction fetch. And this is really memory. This is memory, but like, and we discussed this, like this is part of the memory which instruction are stored. This is part of the memory or data export. So no matter what instruction it is, like we have access to the memory, we should access to the memory at least once, no matter what. And there is no absolutely no instruction that we can execute without having access to the memory, because like all instructions are in memory. Like we have to like read what instruction it is and fetch it and then execute it. So during fetching time, like we need to have access to the memory. We need to like at least access the memory once, at least. This is one Neumann model, and you have it on the hint. One Neumann model. Could be other model where like instruction are not in memory somewhere else, but in one Neumann model, since instruction are in memory and we need to fetch them from memory, at least one memory access are required. Okay, so like easy. So this part, this part of the question, what Mips instruction do not require having access to the memory? None. Like none. All Mips instruction require access to the memory. And Sydney again provided perfect answer for this. Perfect answer. I liked it a lot. This is perfect answer. Since Mips uses a one Neumann model, instructions are stored in memory. This means that during the fetch cycle, a memory access must occur regardless of the instructions. Thus, there are no instructions which do not require accessing memory. However, all instructions except for LB, LH, whatever, these instructions that require having additional access to the memory, which is like relevant to the other memory question, only access memory during the fetch stage. This is a perfect answer, perfect, could not be even like, I could not really add anything to this. This is a perfect answer. Could not get any better. Do you have any question about this? Hopefully this is very clear, okay? And going back to this other question, what Mips instruction require accessing to the memory twice? Like, very simple. Again, like Sydney, again, provided the perfect answer. All instructions require one memory access, since instruction itself is stored in memory and must be retrieved. Beyond this, only the instruction which perform loading and a storing operation not using immediate access memory, okay? All other use registers. The instruction which use 2 cycles are LB, LH, LW, perfect answer. And I mean, this is like perfect answer. And the simplest way you could do it, like you could simply look at this cheat sheet right here. All instructions are here, right? So by default, all instructions use one access to the memory during fetching, okay? What instruction requires twice memory access?
Loading and storing.
It's simple, right? Look at the semantic. This, no memory access, 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 nothing. No memory access, no memory access, nothing, nothing, nothing. No memory access, no memory access, no memory access, nothing until you come here, right? So this load and store operations, where you see mem here, right? Do you see mem? So this load byte, again for LBU, LH, LHU, all of this you see memory, right? SP, SH, SW, right? So all of this, you require memory access, okay? But
I have a quick question.
Yeah.
Aren't registers technically a part of memory? Or are they their own separate thing? Are they in the control unit or memory?
Yeah, good question. And like I noticed that in some answers as well, not really. So when we talk about memory, so in terms of implementation, the registers are implemented differently with flip-flops and everything. Technically, we separate registers from the memory where you store data or instructions. Still, like in terms of operation, yeah, you store things there, right? But we should separate them, right? So like they work like a memory because you store data there. But for good purposes, we separate them because they are way faster, order of magnitude faster than memory access, right? This memory access is slow and like energy consuming, and for all of these reasons that we discussed, like we want to separate these instruction from the rest, where we, like you see that here, for example, the arithmetic operation, and this is for purpose that, for example, we have arithmetic operations that like manipulate data in the registers, right? And that's why we have registers, right? That's why we don't want to directly manipulate data in memory, right? Like if we didn't have any R-type, like we needed to like manipulate data in memory, which is like very time consuming, slow and everything. So like we want to separate this, even though in terms of operations, you could think, okay, like they have the same function. And that's somehow intuitive to think that way, but yeah.
Okay, thank you for clearing that up. I know that was definitely where I messed up on that. I was thinking of the registers as part of memory,
Okay.
and having to access them would then mean that you would need to look into memory.
Okay, okay. Yeah.
I know I also forgot about the fetch step being part of grabbing it from memory. I didn't think that counted as part of the question.
I did
No.
too.
Is there any question?
I was just saying I wasn't thinking about the fetch step either. I was thinking about the actual difference of the instructions.
Right, right. I mean, like, yeah, that's that makes sense. And like, I see the point, and like, even though like we discussed this and everything, and that I see the point why you made such mistake, and that's why we are here, right? Learning from mistakes and learning new things, so it stick. And you know now the differences and everything, and how you need to approach problems and how you need to think about it, right? Again, hopefully this was useful for you guys to think that way, and hopefully this would help some of you who were lost in this. And again, don't worry about the grades and everything, but try to take away as much as possible in this. And I would like to again, you know, highlight the answer provided by Sydney. It was outstanding to see these answers. And for others who answered these incorrectly, I mean, don't worry. I'm sure you will do good in other homework and quizzes, exams. Is there any other questions? Okay, so if not, then have a good weekend. And then I will see. Don't worry about. Don't forget about the homework. This homework is not difficult. Hopefully, you can answer them. Write this assembly program easily. Get a good grade there, and enjoy the weekend. And see you next week. And thanks, and sorry again of what happened last sessions on Tuesday. I was not sure why I was sick very badly.
Thank you.
Thank you. This was super helpful.
Thank you.